This question is from GATE Mechanical Engineering of 2014. This is question number 12 of set 2. The question is, for laminar forced convection over a flat plate, if the free stream velocity increases by a factor of 2, the average heat transfer coefficient, option A, remains same, B, decreases by a factor of root 2, rises by a factor of root 2, or option D, rises by a factor of 4. Let's understand the thermal boundary layer over a flat plate. The formation of thermal boundary layer occurs because there is a temperature difference between the temperature of the surface, Ts, and the fluid temperature. Okay, let's say T infinity. So because of this surface difference, there will be a thermal boundary layer and whose profile may look something like this. Okay, and delta T represent the laminar thermal boundary layer thickness, okay, over a flat plate. And this can be obtained using Ts minus T. T is the temperature at any location, is equal to 0.99 times the surface temperature minus the free stream temperature. Now we can obtain the relation between the heat transfer coefficient and the average velocity or the free stream velocity using Paul-Hyson's formula for laminar thermal boundary layer over a flat plate. Okay, so according to Paul-Hyson's formula, the Nusselt number at any location over the flat plate at a location X, suppose this is the location X from the leading edge of the flat plate. So this is equal to 0.332 times the square root of the Reynolds number at that location into the cube root of the Prandtl number. Okay, and since in the problem we need to find the average heat transfer coefficient, so for average heat transfer coefficient, for average value, we can write the Nusselt number over the flat plate L is equal to 0.664 times the square root of Reynolds number over the flat plate multiplied by the cube root of Prandtl number over the flat plate. Okay, and we know the Nusselt number is given by HL upon K, that will be equal to 0.664 times the Reynolds square root of Reynolds number. So Reynolds number is given by rho VL upon the dynamic viscosity, square root of this, multiplied by the Prandtl number, cube root of Prandtl number, that is mu Cp by K. Okay, now from here we can see that H is directly proportional to square root of the velocity. Okay, that means if we increase the velocity 2 times, that means if the velocity becomes 2 times, suppose V final is equal to 2 times of V, then if we substitute it here, we'll get H final will be equal to square root of 2 times of the original H. That means the original heat transfer coefficient. So if we increase the free stream velocity by a factor of 2, the average heat transfer coefficient will increase by root 2. So from here we can say option C is the correct choice. For more information on thermal boundary layer, you can refer to the NPTEL course lecture number 21, Momentum and Thermal Boundary Layers by Professor S. Dasgupta of the Department of Chemical Engineering at IIT Kharagpur.